working with finite dimensional algebra. So this is a project done at the Max Planck Institute for the Physics of Complex Systems, Dresden, Germany, in collaboration with Professor Dr. the director of the institute, and Professor Dr. Vikiran. So let's get into the talk. So outline of the talk. The basic outline of the talk is that there will be more math than physics in this talk. I will be talking about a hell lot of math and very less physics in this talk, but I will give you an intuition of, I will give you an idea of how to apply this to physical problems, but developing the formalism will be math. So let's, so since we have a good number of first years over here, let's revisit a few definitions that we know. So all of you know what symmetric matrices are. When you take the transpose of a matrix, if you get back the matrix itself, it's a symmetric matrix. So now let me define something which is called a Hermitian conjugate. So if you have a matrix A, you know how to take the transpose of this matrix, right? And suppose this matrix has complex entries. What you do is you take transpose, then take the complex conjugate of each entry of the matrix. The matrix that you finally get back is called the Hermitian conjugate of this matrix A. A matrix is called Hermitian if its Hermitian conjugate and the matrix itself are equal. That's the definition of a Hermitian matrix. A unitary matrix is defined by, if you take the Hermitian conjugate of a matrix, multiply with itself if you are getting the identity matrix, or equivalently, if the inverse of a matrix is its Hermitian conjugate, then we call it a unitary matrix. And orthogonality is just unitary reduced to real vector spaces. Instead of dagger, you have transpose. These are just a few basic definitions. So the prerequisite of this talk was that you guys should know how to multiply matrices. So let's start the business by multiplying a few matrices. So let me define a few matrices. So we have matrix A and matrix B over here, real matrices. Can I square the matrix? What will be A squared? So to square a diagonal matrix, it's easy. All you have to do is just take the squares of diagonals. So 2 will become 2 squared, 4 will become 4 squared. And to find the square of matrix B, you will have to do a little more work, but that's doable. All of you can do that. And once you do it, what you will end up is with these matrices. Fine? Let's do another matrix multiplication. Let's compute A cube and B cube. It's again easy when you are working with A. All you have to do is take 2 cube and 4 cube, which will give you 8 and 64, I guess. B cube will require a little more work, but you will be able to do it. But now suppose I ask you for A power 100 and B power 100, the 100th power of these two matrices. How do you compute it? A power 100 is again fine because all you have to do is take the powers of diagonals. You will get 2 power 100 and 4 power 100 on diagonals, and you are easily, you are happy with the result that you are having. But what about B power 100? One might look for patterns in this, but I don't see any pattern, at least by looking at the first 3 powers of the matrix B. So how do you compute it? You can have a laptop and compute it. That's fine. But with pen and paper, how will you compute it? How long will it take you to compute it? Do you understand the problem? And third years, fourth years would know how to solve this problem. But first years, you guys understand what's the issue over here? So the question is, in the previous slide, we had 2 matrices A and B. The question is, are those 2 matrices completely unrelated? It turns out it isn't. In fact, those 2 matrices are related by this weird relationship. So I define a new matrix S to be 1, 1, 1 minus 1. And if I take S inverse, then I multiply it with the A matrix, which was this diagonal matrix, and then multiply again with the S matrix. What I will get is the B matrix. So if you want, you can take a quick look at A and B. B was this messy matrix, and A was this clean diagonal matrix. So at the first sight, someone who's seeing it for the first time may find this to be really weird. Like, how does it even matter that these 2 matrices are related in this weird way. How will it solve our issue? So let's try to compute b squared using this relationship. So if one wants to compute b squared, what would that be? It will be S inverse AS times S inverse AS. And matrix multiplication is associated. I can first compute S inverse A, then S inverse, then AS. What is S inverse? It's identity, right? Identity. This will become S inverse A square S. Now if I want to compute B cube, what would that be? It will be S inverse A cube S. And now if one wants to compute S inverse, sorry, B to the power 100, this is S inverse A to the power 100. You know what is A to the power 100? It is 2 to the power 100, 4 to the power 100, 0, 0. You know what is S. This is a fairly clean matrix. You can invert it easily. All you have to find is just find the determinant. So even though this weird looking expression is giving us a very nice way to compute the 100 power or the nth power of a matrix. Okay? So even though this expression looks weird at the first sight, do you appreciate that if you know such a relationship between two matrices, you can move or transform from one matrix to another matrix, do your algebra there, where things are easier, come back. How can you come back? Okay, so if you compute A power 100, you move from B to A, compute A power 100, and go back by this transformation, whatever that means. Okay? So this is important. So that gives us, and this is not really important, this gives us what is B power 100. So I just wanted to tell you that these kind of matrix multiplications are really, really important when you are working with in linear algebra or quantum mechanics. So let me define similar matrices. Two matrices A and B are similar if there exists an invertible matrix S such that B is S inverse AS. So we say that these two matrices A and B are similar if there exists such an invertible S. Simple. We saw an example just now. So when you move from B to A by multiplying S inverse on its left side and S on its right side, or when you move from A to B, this is a transformation of matrices. You are transforming one matrix into another, and this transformation is called similarity transformation. So similarity transformation and how similarity transformations represent the change of cases is one of the central ideas that we will be using in this talk. So for the people who understand what a linear operator or a vector space is, you guys know that if you have a vector space and if you have a linear operator defined on that vector space, if you make a similarity transformation on that matrix, it's essentially a chain of cases. So if you don't know that, you can just forget it. But for the people who are here, you guys would know that if I do this kind of a thing on a matrix, and if this matrix A is the matrix representation of some linear operator, this B is the same linear operator but written in a different basis. So in a way, throughout this talk, the two matrices are related by a similarity transformation. I will consider them equivalent. For me, those two are the same because they too represent the same linear operator. I wanted to show you guys how linear operator can be represented as a matrix, but that might be boring for a lot many people over here who have been working with such stuff. But some of your first years and second years would know it by this time. Some of first years, if you guys are interested, by then at the end of the talk we might discuss how we can represent matrices as linear operator. Okay. The most important property is that if you make a similarity transformation, the similarity transformation will preserve many properties of this matrix. First of all, its eigenvalues, its determinant, its trace. Trace is the sum of the diagonal elements, and rank. Forget rank, we don't need it. So we would need trace. Do you guys know what eigenvalues are? Anyone who doesn't know what is an eigenvalue? So because you can prove it easily, but I'm not proving it right now. First statement is that an n-cross matrix can have at most n eigenvalues. An n-cross matrix can have at most n eigenvalues, and next statement will come. You know what is the determinant? I'll just define what is right. Yeah.
It's supposed to be unitary
No. Similarity transformation doesn't concern with unitary or orthogonal matrices. If your S is unitary, then we can replace S inverse with S staggered, and we will call it a unitary transformation. If S is orthogonal, you can replace S inverse with S transpose, and you will call it an orthogonal transformation. But the general setting, the premise that we are working with, is of similarity transformation. I will soon move from similarity transformation to unitary transformation that you are speaking about, because in quantum mechanics, we always work with orthonormal basis, and when we move from one orthonormal basis to other orthonormal basis, we have to move to a unitary transformation. So I will be soon moving to unitary transformation, but up until now, it's just inverse, it's just similarity transformation. So now you guys might, so the earlier example might mislead you to think that, okay, so if I have a matrix, and if I can find an S such that S inverse that matrix times S is a diagonal matrix, then I am sorted. All I want to do with that matrix, I can, whatever I want to do with that matrix, I can compute the nth power of that matrix, I can compute the exponential of that matrix. But is that all you want? Maybe if all you want to do is computations, then you might be happy with it, because you can compute whatever you want. But we as physics students, we want to talk about physics of the problem. So most of it, the physics of the problem might not be directly, you might not be able to read directly the physics of the problem from the diagonal representation. For example, let me show you a Hamiltonian over here. This Hamiltonian is a diagonalized Hamiltonian. You can compute the 1000th power of this matrix easily. But can you tell me some physics of this problem? This Hamiltonian might be representing a real quantum system. Can you tell me any property of that quantum system? Anything? You know the eigenvalues. Of course, you can plot the spectra. But anything physically? Because at the end of the day, we want to talk about physics. That's what we are doing. So let me do a basis transformation to it. At least fourth years and fifth years over here might be able to, and maybe some third years would be able to realize what this physically means right now. Any guesses? Huh? That's not it. This is a very common Hamiltonian that you encounter in condensed matter physics. What is it? It is actually a type binding Hamiltonian with nearest neighbor hopping and next nearest neighbor hopping. And the next nearest neighbor hopping is half as strong as the nearest neighbor hopping. So, okay. For the people who doesn't know what a type binding Hamiltonian is, we have a chain of atoms. Okay, we have a chain of atoms, and electrons on one atom can hop to its nearest neighbor or next nearest neighbor. Okay, it can move to its nearest neighbor with probability. It's not probability; it's called hopping constant. Hopping constant -1, and it can move to its next nearest neighbor with hopping constant -half. So it gives you individually an idea of how strong the hopping is. So here the hopping constant T is -1 and T prime is -2. So the nearest neighbor hopping is stronger than the next nearest neighbor hopping. So I know first year, second year, third years might be lost at this point. What I want to say is that so even though you had this diagonal representation of Hamiltonian, which was easy for you to work with, it didn't tell you much physics about the problem. But as soon as you move to this basis, I don't know what this basis is, but as soon as you move to this basis, you're talking a lot of physics about the problem. You could see that the on-site energy is -2 units. There is next nearest hopping, there is nearest hopping, next nearest hopping, but there is not n hopping. So you could talk about a lot of physics in this problem. So all I want to say is that there need not exist is the basis that will suit all purposes. It really depends on what you need to look into. That depends the basis in which that you have to look at. So what I essentially want to say is that all of these represent inherently underlying linear transformation. When you are changing the basis, what effectively you are doing is that you are looking at the same thing but through different lens. Some lens will give you more clarity when you are looking with a particular aim in your mind, but that lens might not suit other purposes. So I am here in this talk trying to construct such a lens. But when you look through that lens on a Hamiltonian, what you will see is a smooth image. That's the idea of the talk. So now we will state the problem a bit more formally, a bit more mathematically, and we will try solving it. Yeah, that minus will be steep right.
Yes. So like what is the minus and not?
Minus?
Well, what is the minus and not?
So minus. So for that you first need to understand how you construct the type by Hamiltonian, which is not really the topic of this talk. It is quite. So why that negative sign comes up is a big deal there, because what you do is you take the wave functions of this atomic orbital and you take inner product with something sandwiched in between the atomic orbital on one side and atomic orbital on next side. That's how you eventually arrive at this thing. But I don't think I should discuss that right now. Maybe you can ask me this after the talk. For that I have to construct the diagram. So let's get into the business of images. So suppose you have a Hamiltonian. What you can do is you can take the minimum. Okay, consider a real matrix. So you can take the minimum value. So since it's a real matrix, the word minimum makes sense. You can take the minimum matrix entry on that matrix and give it a black color. And you can take the maximum entry and give it white color. And whatever comes in between it, you can give a grayscale. What do you say? A color bar or something. What you will end up with is an image like this. But clearly, this image doesn't have any structure. If you just do this thing in an arbitrary basis by giving this smallest value of complete dark black, and the highest value of white side, what you will get is such an image. You might not see any physics or any structure of the quantum system from this image. The question is, can you make a basis transformation, a basis change, this S inverse AS thing, this matrix multiplication, this brilliant matrix multiplication? Can you make such a matrix multiplication and go to a basis where if I make this image again in that basis, that image will tell me the structure of the quantum system? This image looks ad hoc. It doesn't have any structure or anything. I can't work with it. But if in some basis, will it make sense? That's the question. And if you look at it, see, moving from one pixel to the next pixel, because moving from one pixel to the next pixel, you'll see that there is a huge gradient. It's not a smooth variation, but rather a very rough variation. You are going from a very dark pixel to a white pixel. It's not a very smooth variation, but if we, in some way, find a way in which we can have smooth variations, smoothly varying images, that might give us some idea about the structure of the underlying quantum system. That's what we are trying to do. So that's the question stated here. Can we find a good orthonormal basis? So moving from one basis to another, you require a similarity transformation. To move from one orthonormal basis to next orthonormal basis, you need a unitary matrix, and such transformation will be called unitary transformation. So the question is, can you find a good orthonormal basis or a unitary transformation to go to that orthonormal basis such that the Hamiltonian represented in that basis will give us a smooth image? Once we have the smooth image, the question is, can we have some underlying structure on that image? Can you predict something? Does it have some good properties that would be useful in something? Yeah. Pattern as in? that this pattern or the structure that you're talking about, you will eventually get it once you reduce the roughness of this image or you make this image as smooth as possible. You will see patterns emerging in it. Because if you want to look for patterns, you know that if you are looking for it in a dynamic setting, you can expect that you need this pattern. But if I give you a single harmonic oscillator Hamiltonian, what pattern will you look for? This pattern will depend on each Hamiltonian, right? But now I want to build a scheme that will work for any Hamiltonian. So I'm not sure if any Hamiltonian will have a pattern, because I can call any Hermitian matrix a Hamiltonian. Do you see where the problem is? So to investigate this problem, to build a general scheme, this pattern is a very vague term, or I find it difficult to rigorously define what a pattern is, then find the representation which will have the most, most brilliant patterns. So that's why. But once you find the smoothest form of Hamiltonian, you will see patterns of it. Just take a look. So instead of defining smoothness, I define roughness of an image. So when do you say that an image is rough? So suppose you have an image. So let me just draw a portion of an image. So I'm just taking 4 pixels here. Suppose this is a very dark pixel. This is white. This is very dark. The next image. This is very dark here, slightly dark here, white here, slightly dark here. Which among the following is the smoothest? Second one, right? Yeah. Because moving from a pixel to its nearest neighbor, the variation is minimum in the second one. So that's why we want the second one to be a smoother image. So I define roughness of an image as I take the ij, so an image for me is just a matrix. I just look at so if it's a matrix, I look at the ij entry. I will look at these neighbors of it. I will find the difference between these neighbors. That will give me an estimate of how rough it is when I move from that pixel to the next pixel. Now I will find the difference, square it, and add this all up. That's my definition of roughness. I defined it this way, but you can find that this is already in literature. People have defined roughness of images. Now, what I will do is I will define a matrix here. This matrix is something that you often encounter when you are doing numerical differentiation. So -1, -1, -1, -1, and 1, 1, 1, 0, 0. This is the first forward difference matrix. If I define R to be this first forward difference matrix, then I can write this part of the sum as norm of R8 squared, where this norm is the Frobenius norm. Frobenius norm is nothing but the sum of squares of all matrix entries under it. That's not really relevant. You can forget all these fine details. And this is norm of 8. The second part becomes this thing. You can eventually prove that these two are equal and you will get this. I don't want you guys to understand what this means. All I want you to understand is that what this represents. This represents the variation when you move from one pixel to the next pixel.
Why aren't we considering the diagonal terms?
Why are we
considering the diagonal of, let's say, each ij? So what
why are we not considering the diagonal of each ij?
Yeah.
That's a question that I expected. So for the time being, so now I have defined it as norm of RH square, right? Now I will keep R to be arbitrary henceforth. So if you want to consider diagonal elements, you do consider it and modify your R as follows. Whatever I will be building from now on will be for an arbitrary R. Okay? The formalism that I will be building, that will be for an arbitrary R. Cool? Yeah.
But when we are setting for minimizing the intensity gradient, let's say, in between, like related to a particular pixel square. So, like if we minimize between this and this, then automatically like minimize the diagonal. Because the adjacent is minimized, and that's all.
I mean, see, that's a very intuitive way of explaining it. You are not really introducing that term into your post function. when you explicitly include it into your force function, it might give you a better resolution or a better simpleness. Once you have not done the math, you can't make that claim. I mean, intuitively yes, but you have to do it. Okay. So let me state the problem this way. So what is the problem? We have defined roughness of a matrix as by the way, am I audible at the back? So we have defined roughness of a Hamiltonian as R of H. What we want is the smoothest form of the Hamiltonian, or we want to minimize roughness. So we want to find a unitary transformation U such that R of U dagger H is minimum. This is a question that I am trying to ask. This is just the same thing written in a more complicated. So now I propose an exact solution for this problem. Before that, let me tell you about, so in order to just understand how difficult this optimization, now this is an optimization problem. This optimization problem is difficult to solve because you are working with a non-convex matrix. What that means, I will come to it. Suppose you want to minimize some function, okay? Suppose you want to minimize this function, f of x, comma y, equal to x. A harmless function. This is a function from R2 to R2. So it takes two real numbers and gives me back a real number. I want to minimize this function, but I have a constraint. The constraint is that you can take only those xy's that lie on the unit sphere in two-dimensional Euclidean space. That means that you have R2, which is your two-dimensional space, a plane. On that plane, or maybe on that plane, you can only take points on a circle of radius 1. Now, here the problem is simple because one you will just write it as r cos theta, r sin theta, but I can easily complicate it. But the idea is that usually in such optimization problems, what people use is a technique called gradient descent. I hope some of you at least would have heard about gradient descent. The idea is that you move along the gradient and hope that at some point you will reach a minimum. You usually, it depends on your initial condition, but with a good choice of initial condition, you will reach the minimum. So that's what the crux of gradient descent is. But the problem is that you can't do gradient descent first in this problem because what you do, okay, I'll just show you what you do when you have to do gradient descent. So you will have some function like this. Suppose you are starting from here. You are starting from here. You move in the direction of gradient. You move here. 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 If you move in the direction of gradient, initially you will reach the value. That value will be your minimum. But there is no, I mean, you might reach a mountain as well, but that's also an extrema. It's in general to find an extrema. It can be a maximum or a minimum.
Yeah. In gradient descent, what if we land a local minimum?
Yeah. Gradient descent will most often land on a local minimum only. Because for finding absolute minima, you will have to scan the entire R. Is it?
Okay, but if we find local minimum, but then it is not minimization because there would be.
That's right. I will come to it. I will eventually do something, and I will prove that that something will give me the absolute minimum. You had a question? Fine. So, what is the issue when you are doing it over here? When you are on a sphere, if you move along the gradient of the function, if you are in R2, it's fine because any line in R2 is convex. What does convex mean? If you move from one point in R2, one point in a plane, to another point in a plane, through the line connecting those 2 points, you will remain in the plane throughout your journey. That's what convex means. But sphere is not convex. when you move from one point in a sphere to another point on the sphere, so if you just move through a straight line, suppose you want to move from this point to this point through a straight line in R2, you will go out of the sphere. Or if you compute the gradient at a point of the function at a point and you move along the gradient, you will go out of the sphere. You will go out of the manifold. So you can do descent here. These kind of optimization problems are called non-convex optimization problems. And this problem that we have here is a non-convex optimization problem because similar to moving on the sphere, the constraint here is that U should be unitary. Unitary group is a non-convex manifold. And I know I'm throwing jargons, but all you have to understand is that you can't do descent. If you move along the gradient, you will go out of the space and you won't reach minima. Okay? The very constraint of the transformation being unitary is messing things up here. So what to do? So initially during my project I spent 1-2 days working on this thing. This did give results. I won't say this didn't give results. You have to use a better scheme which is called a Riemannian gradient descent, which you can do in a Riemannian manifold. That's what I did initially. But that gives results, but up to n equals 7. The size of matrix equals 7. But that's not what we want. We want to do it for arbitrarily large Hamiltonians. But here, the algorithm miserably fails in my system at n equals 7. So, what to do? So I thought I would stop doing computation and I will go to math. So what I did is, I used a technique. So we have seen optimized. So at least the physics students here from second year, you guys have seen an optimization problem. We all have seen an optimization problem in classical mechanics. Did you optimize something in classical mechanics? Yes. What? Yeah. Action. We optimized action. We found the stationary point of action or the stationary path of action to find what? To find the actual path followed by the particle. I'll use something here. For that, when you had constraints, what did you use? Lagrange multipliers. I'll use Lagrange multipliers here. I will find an exact solution using Lagrange multipliers. But things will be a little more complex than classical mechanics here because the Lagrange multipliers here will themselves be matrices. I'll have to take derivatives with respect to matrices, which is mathematically a bit more involved, but forget all those math. At the end of all the calculations, whatever you get, it is extremely easy to verify that that is actually the absolute value. So let me state a few supporting theorems. First theorem is the spectral theorem, which says that, so don't read. So here, the initial matrix B that we had in our first slide, we could move to a diagonal matrix through a similarity transformation, isn't it? Can you move from any matrix to a diagonal matrix through a similarity transformation? The answer is no. You can't move from any matrix to a diagonal matrix through a similarity transformation, or equivalently we say that all matrices are not diagonalized. But all Hermitian matrices are diagonalized. All Hermitian matrices are diagonalizable, and there are two more important ideas. If you diagonalize a Hermitian matrix, there will be an S inverse S that will diagonalize a Hermitian matrix, right? That S matrix will be unitary. That's the first important idea. The S matrix will be unitary. And the second most important idea is that once you have done this, you will get a diagonal matrix, right? It will have only non-zero values on the diagonal. All those values will be the eigenvalues of this Hermitian. So what did I say? Every Hermitian matrix, you can move to a diagonal matrix through a unitary transformation. That unitary transformation will yield a diagonal matrix, and that diagonal matrix will be real. Okay? Second supporting theorem is that, don't read this because this is more complicated. So suppose you have two Hermitian matrices A and B. You evaluate the commutator of AB. What is the commutator of AB? AB minus BA. Isn't it 0? AB minus BA is 0, right? Not always. Why? Because it's matrix multiplication, and matrix multiplication in general doesn't commute. But if AB minus BA equals 0, then since A and B are Hermitian, I can diagonalize A, I can diagonalize B. But if AB minus BA is 0, then I can diagonalize A and B simultaneously. What does simultaneously mean? I can diagonalize A with some unitary transformation U1. I can diagonalize B with some unitary transformation U2. If they commute, U1 will be equal to U2. Okay? So I stated two supporting theorems. First one is that any Hermitian matrix is diagonalizable by unitary transformation, and eigenvalues will be there. Second one is that commuting matrices are simultaneous. So now let me illustrate the exact solution using Lagrange multipliers. So this solution is inspired by the generalized solution to the orthogonal probabilities problem by Peter H. Schonman from his 1966 paper. So when I was trying to solve this problem, I wanted to use Lagrange multipliers because of the complexity of RGB. So when I wanted to do it, so I wanted to see if someone had used matrices or Lagrange multipliers in the past. Thankfully, this man had used it previously. So to be honest, I was very inspired by this work to use Lagrange multipliers in my problem. So I used Lagrange multipliers in my problem. And what happened is that, you have to define a Lagrangian. This is not the Lagrangian that you see in classical mechanics. For me, Lagrangian just means a cost function. I want to minimize this cost function. So this is the roughness. I want to minimize this roughness. So this lambda is the Lagrange multiplier. Remember, lambda is not a real number for me. Lambda is a matrix, and this is your constraint. This is how you write the Lagrange multipliers in your classical mechanics. So you have the action to minimize. You add, so it's the Lagrangian plus Lagrange multiplier times the constraint. I'm doing the same thing. But I will take a trace here because you see, this roughness is a real number, and I can't add a matrix to it. I have to add a real number to it. Moreover, when I differentiate this L with respect to lambda, I should get the constraint back. So if I just give a lambda here, that doesn't make any sense. So that's why I have added a matrix. Those are just fine details. You need not worry about it.
What are the event lambda?
Yeah.
What are the event lambda?
What are
Event lambda like the
U is the unitary transformation. That it's a function of unitary transformation. It's a matrix. Lambda is also a matrix.
the matrix that you want to do.
Lambda is the Lagrange multiplier, which is a matrix. U is the thing that we want to minimize. Subject to the constraint you have is minus identity equals 0. What you do is you impose the stationary condition. You plug del u by del L by del u equals 0, del L by del lambda equal to 0. You do a bit of algebra. What you end up with is this condition. So U star is the minimum of this thing. Fine. U star is the unitary transformation that will minimize roughness. U star dagger A U star commutes with B. So what can we say then? By the previous theorem, they are simultaneously diagonalizable. Then you use the fact that they are simultaneously diagonalizable. Okay, I didn't specify what A and B are. A is Hamiltonian square. Okay. P is R transpose R. Remember our R? R was the first forward difference matrix. Didn't I write it somewhere? Yeah, I think I wrote it. Huh? Yeah. So this R matrix. Okay. This is not a symmetric matrix, but remember R transpose R is symmetric for Hermitian. Because R transpose R, the whole transpose is R transpose of R transpose the whole transpose. R transpose the whole transpose is R. So this is a symmetric matrix or Hermitian matrix. I can safely call it Hermitian because all entries of R are big. Fine. Again, that they are simultaneously diagonalizable, both are Hermitian, and you again do some algebra. What you finally end up with is that this U star is EA dagger EB. I know I haven't shown you the details of the calculation because the calculation is quite long. But once you have used this Lagrange multiplier technique and found out the minimum, it is extremely easy to check that this is indeed the absolute minimum. That's a small calculation. I will do it for you over here. But right now, believe me that this is the thing that Lagrange multiplier calculation brings us. So what is EA? EA is the unitary transformation that diagonalizes A. Now the question is, why should A be diagonalized? What was A? H square. This H is Hermitian. So H square is Hermitian. So if it is a Hermitian matrix, it is diagonalizable through a unitary transformation. We have already seen a spectrum here. So EA exists. EB, even though R was a non-Hermitian matrix, R transpose R is a symmetric, hence a Hermitian matrix. So R transpose R is also diagonalizable. So EB also exists. So now my claim is that I claim that the Lagrange multiplier method gives me this optimal solution that EA dagger EB will minimize the roughness of the Hamiltonian. Now I will sketch a short proof of this. You want to look at the R of U star dagger H. This is, I have written here, this is twice of U dagger H. How do you arrive at this? You have to basically use the fact that norm of A squared is trace of A dagger. You have to use this fact and do the algebra and you will eventually arrive at it. Now, what is our U star? U star was EA dagger EB. EA dagger EB. So, what I will get is EB dagger EA A what EA dagger EB trace is invariant under cyclic rotations. So I will just take this EB dagger. Now what was EA? EA was the unitary transformation that diagonalizes A. So what is this? This is trace of, this is the diagonalized form of A. This is the diagonalized form of, because EA diagonalizes A, EB diagonalizes A. Now, if you have, so the product of diagonal matrices is the product of diagonals. So if you have two matrices, you have two matrices, lambda 1, lambda 2, lambda is diagonal, and another matrix mu1, mu2, mu1 diagonal. If you multiply them, what you have to do is just multiply the diagonals. So lambda 1 mu1, lambda 2 mu2, lambda n. This is twice of EADB, so this will be twice sum over I equals 1 to n lambda I A lambda I B. Now there is an equality. So now there is a question: how to order lambda i's and lambda b's? So the idea is that how do you construct EA? You compute the eigenvectors of A and arrange them as columns to construct E. But now, in what order should one arrange the eigenvectors? The ordering is that you should pair the lowest eigenvalue of A with the highest eigenvalue of B. So if you are sorting eigenvalues of A in the increasing order, sort eigenvalues of B in the decreasing order, what you will get is the smoothest form. If you pair lowest eigenvalue of A with the lowest eigenvalue of B, that is, if you sort both in the same order, then what you get eventually is the roughest form. So here, so that is something which comes up from rearrangement inequality, which is an inequality in discrete math, I guess. There is a Wikipedia page on it. So rearrangement inequality tells us that, so you have to minimize roughness. So if you want to minimize roughness, you have to minimize this sum. To minimize this sum, pair the highest eigenvalue of A with the lowest eigenvalue of B, or the lowest eigenvalue of A with the highest eigenvalue of B. What you will get is the smoothest form of the Hamiltonian. Now, I will use another inequality which is called the Ward-Newman trace inequality. Using, let's write this here. Again, even this has a Wikipedia page, you can check it out. Ward-Newman trace inequality, which says that this will always be less than or equal to trace of A. What is trace of A? So, whatever the basis that you are working with, Ward-Newman inequality guarantees you that you can't perform anywhere better than what U star can. U star need not be the unique unitary transformation that minimizes roughness. I'm not claiming that. But whatever U star gives you, that's the best you can do. You can't do anything better. The math guarantees you that. So this is the smoothest image of Hamiltonian. You can't do it. Now let's look at a few Hamiltonians. So what we wanted to read structure of the quantum system from these images. Now the most important question is that does these images have any structure at all? So let's look at the images of a few Hamiltonians and see if it has some structure. If it has some structure, we are happy. The next question is what predictions can we make? Yes.
How can we guarantee that this will give us the smoothest Hamiltonian?
Huh?
How can we guarantee that it will give us the smoothest Hamiltonian?
Because this Ward-Newman inequality, Ward-Newman trace inequality, it tells you that if you have minimized this thing, then so this lambda I, the lowest one paired with the lambda I, the highest one, is less than or equal to trace of this AB written in any basis. And if R of U dagger HU is basically trace of AB written in an arbitrary basis. That's all. Because for R of U dagger HU is trace of U dagger AU. This is U A written in one basis and B written in another basis. The eigenvalues won't change. What Ward-Newman inequality tells you is that this is always greater than or equal to sum over I equals 1 to m lambda I A lambda I B if you pair the lowest eigenvalue of A with the highest eigenvalue of B. So Ward-Newman trace inequality guarantees you that you can't do anywhere better, and this is the simplest. So let's look at a few examples and see if it has some structure. So this is just a quantum harmonic oscillator. This is just this is the diagonalized representation h bar omega n plus half. This is the smooth image representation. Nothing surprising, nothing. Nothing. Let's look at something which is more interesting. Let's look at a type binding Hamiltonian. Let's look at a type binding Hamiltonian with open boundary conditions. Now we clearly do see structure image. We see that so this is the diagonalized type binding Hamiltonian. So this is the image that you get. So Sandeep had asked this question: why are you just taking the nearest neighbor, only the nearest neighbors when you are computing out? So I am using two R's here, the R matrices here. Here I am taking R to be only the first forward difference. Here I am taking R to be the second forward difference. Okay, so I am taking both. I am minimizing each of them. If you minimize R1, you will get this thing. If you minimize R2, you will get this thing. You can clearly see a structure in it. It's not an arbitrary image. It's not just random points and blanks. It clearly has some structure, and it becomes even more evident when you switch on periodic boundary conditions. This is for open boundary conditions. What I will do right now is that I will switch on periodic boundary conditions in this problem. So look at this representation. This is a, if I remember correctly, this is a 1000 cross 1000 Hamiltonian. So what happens if I switch on a periodic boundary condition? I will get a minus t here, a minus t here. You can barely see it. That's a very small change that I am bringing to. I mean, it's a huge change physically, but just looking at it from the perspective of matrix entries, you are just changing two entries in this 1000 cross 1000 Hamiltonian. 1000 cross 1000 Hamiltonian will have 10 power 6 entries. I am only changing two of them. It won't affect. You won't directly see it here, but how will the image change? If the image just represent the underlying structure of the Hamiltonian, the image should change drastically. Because switching on periodic boundary condition is a drastic change in the physics of the problem. This is what I mean. With the same physical parameters, I am just switching on periodic boundary condition, and the image has changed quite a lot. It has changed to this square shaped structure, and this is true even if you vary your coping parameter or on-state energy and so on. So what you can conclude from this example, these few examples, is that this image indeed encodes some underlying physics of the problem and is very sensitive to the structure of it or the structure of the problem. So we have to study the structural properties of that image. So let me take a digression and let me talk about JPEG compression. So we are not talking physics anymore. We aren't talking about math either. What we are talking about is image processing. So let's go to image processing. So JPEG compression is something. So suppose you have an image. It's a huge file. You want to reduce its size. So what you do is you compress it into JPEG format. So this is the same image with 50% lossy compression and 80% lossy compression. Can you identify some difference between these three images? They all look the same, but it is compressed. So look at it. The first image, it has a size of 824 kilobytes, and the last image is just 38 kilobytes. That means you have lost almost 90% of your information, right? So you have to look for 80% of your information. So you have lost a huge part of the information. What did you do? You have clearly lost something, but it is barely visible, right? Barely visible. So it's just that our human eyes are not able to detect it. So the idea is how JPEG compression works is that it works on a property of our human eye. Human eye is not sensitive to high frequency variation. Human eye is only sensitive to a certain level of low frequency variation. So what we do is we move from this image to its frequency domain, and for that we use a discrete cosine transform. So this is the image. This is a black and white image, a grayscale image. You group this into 8 cross 8 pixels. That's sometimes able to in image processing tools. Let's forget it. They do a discrete cosine transform. Why do they do discrete cosine transform? They move to the frequency space. Now in the frequency space, what they do? They only take a few low frequency components which lie on the top or left half of the discrete cosine transform. Everything else they put it to 0. And they do a inverse discrete cosine transform to get back the image. Fortunately, our human eyes, fortunately or unfortunately, our human eyes are not sensitive to those high frequency variations, and we don't see it. But the size of the image goes down considerably. That's what we saw in the previous slide. Now the question is, why am I talking about this? What does JPEG compression has to do with quantum Hamiltonians? So what was our unitary transformation? 8 square. A is a similarity transformation that diagonalizes 8 square. If a similarity transformation diagonalizes 8, for example, suppose S inverse 8S is B, then what is S inverse of 8 square S? What I can do is I can write it as S inverse of 8S. I can plug in an S inverse here, which is identity. This will be D, this will be D, so this is D square. So what I can say is that any unitary transformation that diagonalizes H will diagonalize H square. So what I can do is I can replace DA as EH dagger EB. Now a question will be that, is this unique? Because you are taking a particular EA. This is unique under certain cases. I'm not. So I have studied uniqueness of this image, and I clearly have proofs of when this image will be unique. But I won't be discussing it here because it has a lot of subtleties. To discuss about uniqueness, I will have to do maybe many proofs and all, which will be quite boring for you guys. So I thought I would just not talk about uniqueness. But certainly this is one of those smooth images. So what will be the smooth image then? It will be U dagger HU. This will be EB dagger EH dagger EB. Now what is EH dagger? It is the diagonal form of H. Now there's a catch. You have to order this B matrix, this diagonal matrix, in the decreasing order of their eigenvalues in the decreasing order of their absolute values. Because we found from this whole Newman trace inequality that it should be paired in that way. This EB by definition, by the standard definition in literature, will have eigenvalues in the increasing order. So the other one should have in the decreasing order of their absolute values. So the idea is that here this B is diagonalized by the discrete cosine transform matrix. So this EB that you see over here is exactly the discrete cosine transform matrix that you see in image processing. So what you are doing is the discrete cosine transform that you had in your DCT compression, or it's been used a lot in image processing, and that same discrete cosine transform pops up here. But the even more interesting fact is that how are the eigenvalues in D ordered? It is ordered in the decreasing order of their absolute values. What was our idea of natural image in discrete cosine in JPEG compression? A natural image in its DCT will have a dominant top left corner. The first few eigenvalues of the top left corner will be dominant. Here, whatever the math gave us, it is dominant in the top left corner only, because we are ordering it in the decreasing order of their absolute value. So it is a very nice way in which the image of the Hamiltonian that we get out of this formalism agrees beautifully with the definition of natural image in image processing. So one can call this image of the Hamiltonian indeed a natural image according to the definitions of image processing. So it has a lot of symmetries. The image will be symmetric with respect to this diagonal. It will be symmetric with respect to this diagonal. And if you take the center of this matrix and take a reflection of any matrix entry with respect to this center, you will get the entry again. So that is called centrosymmetry. It is symmetric with respect to center. This matrix has a lot of such symmetries, and this matrix also has a tuplets angle decomposition, which is quite important, but I don't think I will have enough time to motivate why it is important. So this matrix, this smooth matrix, you can write it as the sum of a tuplets matrix and a angle matrix. This tuplets matrix is a matrix which has constant diagonals, which means that in each diagonal you will only have one value. Repetitions of that. Angle matrix will have constant anti-diagonal, and this smooth matrix is a sum of tuplets and angle matrix, which means that that this has a lot of redundancies, and there's a way of dealing with this redundancies to reduce the size of the image. You can reduce the size of the image. In a way, you can compress the information in the Hamiltonian. I don't think I'll talk about it, I'll just skip through it. These are just the reduced images. This is a 100 cross 100 Hamiltonian. This is the reduced image. You can see some variations here. This is so a 100 cross 100 Hamiltonian is now reduced into a 10 cross 10 an image of size 10 cross. Final thing that I want to talk about today is what's the use of this? How will this be useful in noisy systems? So maybe can I take 10 minutes? So suppose you have a noisy image. You have grains on image. Forget quantum Hamiltonian again. Let's go back to images. So see, that's what the elegance of this thing is. You can work with Hamiltonians the same thing people work with images in image processing. Go to images. Suppose you have noise on images. What do you do? Yeah, you of course try to remove it, but how? So the most common technique is using a mean filter or using a blur. What you do is, so if this is your image, you construct a new image, but whatever the value is in that pixel, you replace it with the average of a neighborhood of that pixel. Okay? You replace it with the average of its neighborhood. That is the idea of denoising by blurring in image processing, and people have worked a lot on it. People are using it every day. Okay? You download any image processing software, simple any editor, and you will find something like that. So it's just an image. It has so the original image. You can see a lot of grains on it. You apply a mean filter, it reduces the noise. It's just different types of filters. Doesn't matter. You can clearly see that the noise is reducing. I don't know if you can see it from the back, but believe me, it's reducing. Can we apply a similar technique to Hamiltonians? See, when you are trying to realize a Hamiltonian physically, what happens is that noise will be appearing in your matrix entries. But these noises, you don't know how bad it affects your eigenvalues and eigenvectors. You have no clue how bad it affects your eigenvalues and eigenvectors. Can you just use a similar blurring tactic to your images?
What's the noise?
Huh?
What's the noise in it?
Take it to be Gaussian output. Take it to be Gaussian. Okay? Gaussian output centered at 0. Because I want with some standard deviation, because I want plus minus to cancel out when I am taking the mean. That's the idea. And most noises that we encounter in our surroundings are Gaussian and centered out. Okay, can you do it? Can you? So I give you a noisy Hamiltonian. You could do it for your image safely. If I give you a noisy Hamiltonian, can you take each entry of the Hamiltonian, replace it with the average in its neighborhood, and say that yes, now I have my denoised Hamiltonian, both. Can you do it? Assume the noise is still the same noise on your image. Can you do it? Let's say it's Hermitian. Let's say it's Hermitian. It will be Hermitian. Let's say it's Hermitian. The problem is that for an image, all you care is how does this image look. If it looks smooth, you are happy. But for a Hamiltonian, you care a lot about its eigenvalues and eigenvectors rather than how the Hamiltonian looks. That is something that is more important to you. If averaging gives you a nice looking Hamiltonian, a nice looking image, but if it alters the spectrum of this Hamiltonian entirely, then blurring is absolutely useless in this Hamiltonian setting. So the question is, does it affect the eigenvalues and eigenvectors? Indeed it does. Just take a random Hamiltonian, you do this blurring, you will see that it will mess up your eigenvalues and eigenvectors. But now comes our smooth representation, the image representation. This is what people in image processing does. Now we have image of Hamiltonians. What happens to the eigenvectors and eigenvalues of the Hamiltonian if we do blurring? Where? In our smooth image of the Hamiltonian. Because the smooth image of the Hamiltonian has information, entire information about the eigenvalues. So let's see what it happens. So I state So defining how I define blurring is that so similar. If you are using the first definition of R that I gave you, all you have to do is replace this entry by an average of this entries. You can take any k neighbors, m neighbors that you want. So some over k equals 1 there, you replace it with the average. So question is how badly it affects it Hamiltonian properties. So the first theorem, which I was doing the math, I got this result that I was totally surprised by it, so I did it once again. So the first result is that if you blur your smooth images, the eigenvectors remain invariant. If you blur, you take any neighborhood, and blur your image, but in this basis, it won't change the eigenvectors of your Hamiltonian. Now the question is, will it change the eigenvalues? It will, but it changes in a very nice way. What happens is that the kth eigenvalue just gets multiplied by a constant. So the new kth eigenvalue is just a constant times the old eigenvalue. So what happens is that if you consider your new eigenvalues as a vector, this is a linear transformation of the non-blurred eigenvalues but this linear transformation is diagonal. There is no mixing of eigenvalues there. So it's a clean way in which eigenvalues transform. And you can always invert this to get back your old eigenvalues as well. So the eigenvectors remain invariant was a very, very strong result that gave us the freedom of blurring the images of Hamilton. More interestingly, what happens is that if you go to the large n limit, this factor that you see over here, if you go to the large n limit n going to infinity, irrespective of what your m is, that is, irrespective of how large your neighborhood is, if you make your Hamiltonian large in the limit n going to infinity, this prefactor will become 1. What does that mean? Lambda k tilde equals lambda k, which means that in the large n limit, both eigenvalues and eigenvectors of the image remain invariant under blurring of any order. So whatever people working in image processing have been doing since years, you can now do it with Hamiltonians. All you have to make sure is that you take the image representation of Hamiltonians and we devised it. Clear? So that's the chronology here. So let me summarize. We propose a mathematical framework where we can map Hamiltonians into images. We showed using discrete cosine transform that the transformation, the image that the map, the Lagrange multiplier solution gave us, indeed respects the definition of natural image in image processing. The image representation has several structural properties like the Toeplitz angle decomposition and a lot of symmetries. And the eigensystem of the Hamiltonian is robust, it is very less affected, and in the large n limit is not affected by blurring, which is a very, very strong statement. Future directions, this work has not been completed, we are working on it even now. So our future directions is that we will try to develop a denoising algorithm for Hamiltonians and maybe density matrices as well, using these based on this image processing techniques, particularly blurring. We are interested in extending, so this image of an n-cross n Hamiltonian lies on an n-cross n grid, right? It's an n-cross n grid with n squared pixels. This is already done. So using Chebyshev interpolation, it's not that I interpolate it, but the mathematical form that we get out of it is exactly the form of interpolation. So why not interpolate it? So one can use Chebyshev interpolation and get it into a continuous image on a square. That has already been done. And there's another thing that we want to do is that you already saw that in time binding Hamiltonians, this image respected the structure of the Hamiltonian, whether it's open boundary condition or periodic boundary condition. So the question is, can you decipher the symmetries and maybe the boundary conditions or some physics of the quantum system by looking at the image of the Hamiltonian? This is the third question. We have some progress on the first two. Second thing is completely done. On the first one, this one is something that we are even puzzled about right now. If you have some suggestions, I would be really happy to hear about it. So those are the future directions. References. you can read about, so this is optimization on smooth manifolds, the other optimization that I talked about from the first one. So I told you, right, our human eye is not really sensitive to high frequency variations. That has been rigorously studied by this paper. Now, this is about JPEG compression only, and this is the paper that helped me the most, the paper by Vikiran about the solution of the problem. And that's it. Thank you everyone for showing up. Thank you for listening, and thank you for the love for the subject. I'll take questions now. Yeah.
What motivated you to like start with like Hamiltonian?
Huh?
What motivated you for this idea? Like,
Professor Rose, my super, it was his idea, not mine. So he motivated me to look into it. It is not a project that I proposed, but a project that he proposed. Anything else? So yeah, that's it. Thank you. If you want to ask something, I'll be around.